Are anybody going to introduce or anything? Or
Yes, yes.
Okay, we are live.
Okay.
Good morning, everyone. We heartily welcome you to the second day of PROTOLITH 20. We sincerely hope your excitement and zeal has only increased since yesterday, and your experience with us so far has been good. Today, we have a very special speaker to open our event. He is one of the treasured alumni of the Department of Earth Sciences, IIT Bombay, who graduated in the year 1968. I would now request our distinguished head of the department, Professor Shantanu Banerjee, to extend the welcome to our first esteemed speaker of the day, Professor G. Shanmugam.
Good morning, everyone. It is my pleasure to introduce Dr. SHANMUGAM, who graduated from IIT Bombay in 1968 in the field of MSc Applied Geology. He has done tremendous works on this deep water processes and deep water sedimentation, and he completed PhD from University of Tennessee in 1978, and then joined Mobil Oil Company and stayed there since his retirement. But being in industry, he continued to research on deep water processes, and he's a very proud Indian, although he is an American citizen. He always tries to help Indian sedimentology community, stratigraphic community in any form. So you can approach him, and if it is of academic interest, he is always ready to help. The mainstay of his research is that he always questions what is written in the book. So that is important. Don't believe that whatever is written in the book is correct and do not require a reinterpretation. So in his talk, you will realize that how important it is to question if there is any irrational, irrelevant ideas that needs to be questioned, and that he has done always, and that's why his name is always associated with deep water sedimentology. He has already written 5 books on deep water processes and more than 100 papers in journals. And without wasting time, I now request Dr. Shanmugam to deliver his speech.
thank you, Professor Shantanu Banerjee. It's a great pleasure to be here as a proud alumnus of IIT Bombay. Good morning, everyone. First of all, let me welcome you all to PROTOLITH 20 webinar. The topic I have chosen today is transforming obstacles into opportunities by breaking up of orthodoxies in process sedimentology, physical oceanography, and petroleum geology. I'm going to do this using case studies. This book was just published last month. It is called Mass Transport, Gravity Flows, and Bottom Currents, Downslope and Along-Slope Processes and Deposits. It has 540 case studies, and I have cited 1,612 references. It's a thick book, and students who do research on deep water sedimentation, they may find this book very useful. Today, I'm going to tell you a story using 35 case studies stretching 46 years, starting from 1974, when I started my PhD dissertation. This story has historical, philosophical, personal, experimental, empirical, and global components. The number you see on the right, on the left-hand side, is the number of case studies. As the story unfolds, you will see various numbers that represent the particular case study. The last time I gave a talk like this at IIT Bombay, it was in 2003. It was called Institute Colloquium. At that time, Professor Chandrasekharam was the head of the department, and he wanted me to come and participate in this colloquium. They organized this in this main auditorium at IIT Bombay. It was packed because many people from ONGC office in Bombay came, and other people from all over Bombay came to the function. At that time, I talked mainly about the turbidite paradigm. But today, I'm going to talk about a variety of topics. I purposely chose 35 case studies. I want to give you a sample of how complex geology is, how to deal with them. Throughout my career, I considered these sedimentologic oceanographic pioneers as my mentors: Bagnall, Sanders, Klein, Shepard, and Hollister. Bagnall was a British engineer. He was the first one to put clarity into the definition of turbidity currents. Sanders was the first one to recognize the stratified flows and their importance in stratigraphic record. And Klein, who introduced the concept of deep water tidal sedimentology. Shepard, who measured tidal currents in submarine canyons. And Hollister was the first one to introduce the concept of contour rights from his PhD thesis at Columbia University. Of these three, Sanders, Klein, and Hollister, I have had professional relationship with them. Sanders reviewed my paper called The Bama Sequence and the Turbidite Mindset. It was published in the Earth Science Reviews. Klein reviewed my paper on the Krishna Godavari Basin for Journal of Sedimentary Research. Hollister reviewed my paper on bottom current sands for the AAPG Bulletin. In all my publications, I apply this doctrine of uniformitarianism, and I will do that today also. Before I go into the topic, I would like to briefly introduce myself about my background. I was born in a small town called Simari in southeastern India. I went to Anomaly University, received my bachelor degree in geology and chemistry from 62 to 65. Then I went to IIT Bombay in 65. Why did I go there? Why would I go to IIT Bombay? I didn't know anything about IIT Bombay at that time. After I received my bachelor degree, I got a teaching job as a science teacher in my local high school. And normally, that would have been the end of my life. And I received a postcard from the head of the Department of Geology at Anomaly University, Professor T.N. Muthuswamy Iyer. The postcard said, "Come see me." That's it. So I went and saw him. He said, "What is your future?" I said, "Sir, I got a teaching job in a high school. I am settled." He said, "No, you are not settled." And he said, "You are going to go to IIT Bombay. They just started a new course called Applied Geology in 1964. I'm talking to him in 1965. And he said, "This is an important course. You are the right person to go there. You passed in first class. You are a ranking student. I don't want to waste your life as a teacher in Sirgari." And I told him, "I'm from a poor family. There is no way my parents would allow. We don't have any money to go to IIT Bombay." He systematically explained to me the importance of going to IIT Bombay. He convinced me, so I got a loan and I went to IIT Bombay. Actually, he was right. I did very well. I got first rank. They even gave me a medal. But that's not the most important part. The important part, what happened to me, I went through a total metamorphosis. That is the correct word for this. When I went to IIT Bombay, I was going to get a degree and get a job in India and be a good geologist. That's it. But after going to IIT, that was the first time they were offering this course. I was the second batch, and I was required to take courses like engineering geology, soil mechanics, petroleum engineering, Russian language, because it was sponsored by the Soviet Union at the time, landslide exercise, ONGC training in Ran of Kutch under Dr. S.K. Biswas. He later became a professor at IIT Bombay and ONGC lab training in Ahmedabad. MSc thesis under Partsani. It's in sedimentology. And CSIR research scholar in sedimentology. All this made me into a totally different person, wanting me to go to USA and get my PhD. So this is a total metamorphosis, what happened to me. So I did go to USA. I did my master's degree at Ohio University. There was a diagenesis project. Then I went to University of Tennessee. I joined the program, PhD program under Professor Kenneth Walker. And he's a very pragmatic, no-nonsense, field-oriented professor. And I try to follow him in my own profession as much as I can. The purpose of the PhD thesis was the origin of Middle Ordovician severe shale. It was a critical piece of information to understand the Appalachian geology. It has got more than 2,500 meters of shale, and it has implications for tectonics, stratigraphy, and sedimentology. Normally, when you do a project, say in sandstone, you go to the outcrop, you look at the bed, measure the thickness, grain size, normal grading, cross bedding, Hammocki cross stratification, you take notes and so on. But that you cannot do in the severe shale because there is nothing to see in the outcrop. It's a kind of bunch of rubbles all over. It's difficult to sample because it's shale. When you hit the rock, it goes into pieces. So I had a major observation problem. So I used to apply epoxy resin on the outcrop and wait for 30 hours for the resin to cure, go the next day with a rock saw and cut the rock into small pieces. And then you bring those pieces of rock to the lab. Then you make polished slabs, acetate peels, thin sections, X-radiographs. Then you see things. So you have an in-between, very strenuous, tedious, time-consuming job even to see the structures, which you normally see in the sandstone. So that was the biggest challenge I faced. But my professor told me, if you go through this, whatever you are finding, it's going to be very critical to understanding not only the local geology, but regional geology. So this is one of the pieces of the polished slab. You can see the projected clast that comes from that part of the basin on the left-hand side. And so when I look at these various slabs, thin sections, and so on, I recognize debris, turbidites, contourites, soft sediment deformation structures. Then I analyzed manganese. Then I did subsidence analysis. So at the same time, TSDP was they drilled Site 262 in the Timor Trough of Australia. When you look at the core, that looks very much like the Sevier Basin. And there are other similarities in terms of tectonics. So we proposed the TSDP site 262 of Timor is very much like the Sevier Basin. Therefore, we proposed that this is a 4D basin. So when I was doing all this in Tennessee, Gary Lash in New York, he was studying the Central Appalachians. And he was coming up with similar story. So we compared the Central Appalachians with the Southern Appalachians. We published the paper, Analogous Tectonic Evolution of the Ordovician Fordips, Southern and Central Appalachians. It was published in Geology. When it published, it was a very controversial paper. Now things cooled off. Now they accept our hypothesis. And because of this kind of work, I was able to publish 7 major articles from my PhD thesis. And plus, I collaborated with Doric Stowe. He's a very well-known sedimentologist from England. And we wrote a paper on fine-grained turbidites and so on. Because of these publicity and so on, I got a very good job with mobile research in Dallas. So this is one of the first case studies where you overcome obstacles and that provides opportunities to publish papers and even get a job. This is the research laboratory in Dallas, mobile research. The figure on the top is the very first lab I did research on. I worked on basins in Australia, New Zealand, Alaska. As you can see, the building is not very impressive. It was a functional building. Mobil was the second largest oil company next to Exxon in 1970. They wanted to expand the research facility in Dallas. They did have a research facility in Princeton, New Jersey. That's mainly for doing research on zeolites, refining, and things like that. So they allowed a lot of money. They hired I.M. Pei, a world-renowned architect, to design the research building. I.M. Pei was the one who designed Louvre Pyramid in Paris, France, for the Louvre Museum. He was the one who designed the Bank of China in Hong Kong. He has designed buildings all over the world. There is a YouTube documentary on buildings he designed and so on. Anyway, he was the one who designed this building for mobile. That's where I did most of my research. I did the work with Dick Mayola on the Washi Tape fish, with Jed Dammit in the North Sea cores, the Norwegian Sea cores, Nigeria, China, and so on. Then I moved into the third research facility from where I did the research on Gulf of Mexico, southeastern France, the unknown sandstone, Ecuador, Gabon, Brazil. Then 2000, I retired. I started teaching courses at University of Texas at Arlington. I also started consulting for Reliance Industries in Mumbai, then PetroChina in Beijing, and so on. So one of the first projects I did for mobile was this Gippsland Basin, Australia. That's on the southeastern corner. The orthodoxy at the time, cumic coal can generate only gas. They cannot generate oil. But this basin had oil field, gas fields, some of the big oil fields like halibut and kingfish. So they have 3 billion barrels of oil in this basin. But there is no marine source rock to generate oil. So where the oil coming from? So that's the objective of my study. One of the first thing I did was to understand the paleoclimate. At the time of deposition of the oil field and the coal basin in Australia, the northern New Zealand was in a similar climate, similar vegetation, and so on. So because the coal is the primary source, in the Gippsland Basin. I went to Australia. As you can see in the bottom photograph, this is one of the thickest coal seams. It's 165 meters thick. When you look at in close up, it has got resin balls coming from a species called Agathis australis. You have plant remains, stems belong to that particular plant. It was very unusual, very exciting. So I collected samples and so on. So to understand how this kind of coal formed, you go to New Zealand. That's where I went, near Auckland. And this is the kind of tree Agathis australis grow in New Zealand. They grow up to 50 meters tall, 13 meters girth. They live up to 2,000 years. They have been on Earth since Jurassic. So that's all very exciting. So I wanted to know more about these plants and their organic matter and so on. So we went to the forest. I wanted to collect leaves from the very mature trees. But these are very tall trees. I don't climb trees. So we brought a forest ranger with a shotgun. So I'll tell him what limb from which I want the leaves from. He will shoot the leaves. And this is the kind of leaves will falling down. Then I will collect the samples. I brought that sample to Dallas. I studied under a scanning electron microscope. As you can see, they have very thick cuticle. These are wax coating. Why it is important? Cuticle is the source of waxy crude oil, and they form long chain paraffin wax called alkanes. So I brought coal. We did hydrospiralysis from the yalon coal. And hydrospiralysis is essentially extract like oil-like substance. And you do gas chromatograms. And you can see the long chain normal alkanes. And they are very similar to what you see in the kingfish oil field and the halibut oil field. So now we can establish that this oil is coming from coal. So I propose this model, kind of subsiding basin with kauri trees growing. They accumulate pile of organic material, therefore they form thick coal seams. And I apply the uniformitarianism. You start with the rainforest, you form coal, then you go to oil. So it's a very straightforward connection. So I published this paper in the AAPG Bulletin in 1985. Even today, this has been one of the most cited articles. So in this case, the orthodoxy was you cannot generate oil from coal. I tried to show, and I did show, that you do generate oil from coal. So that's one of my first case studies for Mobile Oil Company. The next case study is the Prudhoe Bay field. This is the largest oil field in North America. They have 25 billion barrels of oil. The oil field in the northern part of Alaska. And I published a paper with John Higgins, and in that, this was also published in AAPG Bulletin. We documented the porosity is secondary, not primary. So that's where I'm breaking up the orthodoxy in this case. So to understand what's going on here, the red zone is the reservoir itself. That's called the Permo-Triassic Ilishek Formation. The yellow line is the Neocomian unconformity that comes and truncates the reservoir where the oil field is. This is significant to the story. So this is a typical section of a log and a core. The core is composed of braided fluvial strata. It has got some deltaic low sinuosity streams. These are all coarse grained material. So that's a typical log on the lithology. When you take a hand specimen and polish it, this is what you see. It's composed of chert grains, microcrystalline quartz. If it is black, it is fresh. If it is white, it is altered. And there are in-between grains with the rims on. So you see a variety of alteration of chert grains. When you see this under the microscope, this is the unweathered chert, this is the rim, and if you are not familiar with the porosity type, primary porosity is the depositional porosity. This is how a depositional porosity looks like between grains. That's the conventional wisdom. They thought all the porosity in this rock were primary. They do occur. But what is more important is the secondary porosity. Why I call it secondary porosity? You can see the clear rim like that. There was a grain that got dissolved out. All you see is a hole. The blue area is the porosity. See, there is another one there. There's another one there. It's all over the place. So the primary porosity is a very minimal part of the story. So I propose this. You start with a fresh chert that is black. Then you go to a rim. That's the second stage. Then you go to complete alteration. Then you totally dissolve out the grain, just forming a whole porosity. So we published this in the APG bulletin. The next is how it forms, why it forms. Again, go to Paleoclimate. When you do that using vegetation, climate, and so on, southern China is the best possible analog for the timing of the unconformity in Alaska. This is the city of Guilin. This is the Lee River. So I'm going to take you on a river ride, boat ride along the Lee River in China. And when you go to Guilin, this is what you see, large pillar karst. This is the Lee River, and that's the karst. It's all in limestone. Remember, I was talking about a sandstone in Alaska. Now I'm showing you the limestone karst in China. And there are large caves as you go along this Lee River ride. And there's a man standing here for scale. In the cave, he may argue that man is small in size. Still, it's a large cave. I think of it as a large porosity. There is karst in Australia, where the composition quartzite is not limestone anymore. So I propose this scenario, the near-common conformity, where you have dead animals, they have bones rotting, and you have a lot of trees, and these meteoric water, they go into the reservoir and causing dissolution of the quartz, microcrystalline quartz. So it's a meteoric water dissolution along the exposed surface. There's one other piece of evidence. When you plot the one zone, that's zone 4, that's the braided channel facies, there's more or less the same grain size, but the porosity gradually increases as you come closer to the unconformity. That means the dissolution, the degree of dissolution is increasing towards the unconformity. That you can see in thin section. So there is another break up of orthodoxy, in this case diagenesis. The next orthodoxy is before 1987, sedimentologists thought the fan delta and braid delta are all one and the same, no difference. They use the term fan deltas for everything. Then John McPherson myself and Mayola published this paper. I'm sorry. Published this paper in the GSA bulletin. We distinguish fan deltas from braid deltas. In fan deltas, the dominant deposit is mass transport deposit, only cohesive debris flows and so on. In braid deltas, it's fluvial, braided channel, a lot of reworking and so on. So why it is important? It is important because in terms of reservoir quality, this is not such a good reservoir because you have a lot of mud and stuff. This is a better reservoir because you have a lot of reworking, removal of mud. So it makes a big difference for oil company people. So you can't lump all this together and call everything a fan delta. So McPherson et al. Introduced this concept of distinguishing fan delta from braid delta. This is how a fan delta looks like. This is from Baja California. This is how a braid delta looks like. This is actually a photograph by McPherson. Incidentally, he is a top-class sedimentologist. He is from New Zealand. He had thousands and thousands of pictures like this. He was kind enough to borrow one of these. The next orthodoxy, we normally think sediment comes down slope, goes into the deep ocean, forming submarine fans. That's all fine, they do happen. There are also exceptions which we must pay attention to. This is one of those cases where the sediment comes out of a river and then take a right turn instead of going all the way down to the deep sea or going to the Pacific Ocean. So I published a paper in the Journal of the Indian Association of Sedimentologists just last year on the global significance of wind forcing for hyperpycno flows, whether it's in sediment transport and provenance and so on. So if you pay attention to these oddities, then you are in a better position to predict what's happening in the geologic record. This is the model I proposed. The conventional wisdom is you go from the source to the sink. Sediment goes directly from the land to the shell to the base, slope and to the base. The example I just showed you, you take a turn, it goes here. So if you want to predict, you have to know these exceptions as well as the norms. Okay, I've been talking about mainly in the subaerial processes and so on. Now we are going to go into the deep water. One of the common processes are slide, slump, debris flow, and turbidity current. In terms of sediment transport, coarse grain, slide, slump, debris flow, they are more important than turbidity currents. Turbidity currents are popular, but they are not important. Middleton and Hampton proposed this classification of sediment gravity flows based on sediment support mechanisms. Debris flows, grade flows, fluidized flows, turbidity currents, and so on. I propose sandy debris flow for a region between debris flow and grade flow. We have to know some of the basics of fluids, their differences. One of them is fluid rheology, that is the stress-strain relationship. If there are two major fluids, one is the Newtonian, the other one is Bingham plastic. The Newtonian, when you apply stress, they tend to deform immediately. The Bingham plastic, you have to pass the yield strength, then it begins to deform. The Bingham is the debris flow, Newtonian is the turbidity current. We have to know this because physics, they don't change with time. So you can apply the uniformitarianism, whether it is the Cretaceous or today, It doesn't change. Similarly, from experiments, you can learn a lot from, and we introduced debris into the flume, and what they do, as they move down slope, they form the basal debris flows and upper turbidity currents. These are stratified flows. This is what Sanders distinguished. They are not one and the same, but some people tend to lump all this together and call high density turbidity currents. In a true turbidity currents, they are fully turbulent. When they deposit, they form normal gradient. In outcrops, they form beautiful sheet-like. When you go to Spain, northern Spain, take a trip to Zumaya Beach, this is what you'll see. Then the contours. People lumped the turbidity current and basal laminar flow that I mentioned John Sanders made a distinction. They lumped them together, called it high density turbidity. Let's see what that means. When people say high density turbidity current, that means one flow has a higher density than the other flow. Density is controlled by sediment concentration. Let's look at the published values. According to Badnall, typical turbidity current has a less than 9% sediment by concentration by volume. Low density turbidity currents goes from 1 to 23. High density goes from 6 to 44. Debris flows go to 20 to 60. So if your flow has 20% sediment concentration, you could classify that as a debris flow, or a high density turbidity current, or a low density turbidity current. So then the term high density turbidity current doesn't make any sense. So I wrote a paper called High Density Turbidity Currents. Are they sandy debris flows? It was published in Journal of Sedimentary Research. After it was published, there was a lot of commotion. People say, oh, this is not right, and you are wrong. And they took a survey from 1996 to 2003. And they found out that this paper I published is the single most cited article during that survey period. The results are published in the International Association of Sedimentologists newsletter, August issue 2003. Now, if I'm wrong, why all these people are reading this paper? More importantly, why are they citing? So the point is, when there is an orthodoxy, if it is in error, you should point out by breaking the orthodoxy. There is one side note. When I submitted this manuscript to Journal of Sedimentary Research, the editor-in-chief at the time was one Professor John Southern. He was a professor at MIT at the time. He sent it out to review to 3 people. One said maybe, one said reject, one said not really, but the associate editor said reject. John Southern, the editor-in-chief, overruled the decision by the associate editor, and he published. I think sometimes controversial papers are difficult to publish. Once you publish, they get attention. Then go to another controversy. This is the Washi Tape fish. It's in Arkansas and Oklahoma. Orthodoxy, they are classic North American turbidines. Maiolo and I published a paper in the AAPG bulletin, and we said, no, they are not. We studied rocks in Oklahoma and Arkansas. When you look at the rock, this is what you see, the quartzite pebble. They occur next to smaller quartzite grains. If it is a truly turbulent flow, then the larger grain will settle, smaller grain will float. You'll see a normal gradient. You don't see that. Here it's all mixed up, suggesting the flow had strength, like I was talking about earlier. So it's a debris flow. And they form this abrupt ending of the bed. It's more like a snout of a debris flow by freezing. Then you have a lot of floating clast. They're typical of debris flows. And you see these big blobs floating around. They're debris flows. Then you see these duplex structures. You can see in this case it dips to the left, this case it dips to the right. But people thought these are tectonic duplexes. The problem with that is when you have opposing dips in adjacent beds, tectonic forces don't change courses like that. But you can explain them by sedimentary processes, like slumping. That's what we did. We published a paper in geology, myself, Mayola, and Sales in 1998, explaining this. We also conducted experiments supporting this idea. So experiments are always important. When you don't know something, the best thing to do the experiments. So in the 1980s, Mayola and I published papers calling them all the turbidites. Then we have been doing that, and then the data accumulated. We worked for nearly 10 years. Finally, we reached a point we can no longer call them turbidites. We had an epiphany. We changed our mind. I said, 1995, we published this paper calling they are debris and slums. This caused a lot of commotion. People say, how dare you do this? This is not right. This is a classic North American turbidites. So all these geologists, sedimentologists, there are discussions. And some of the names are very big names like Arnold Baumann, Don Lowe, Roger Slack. So it published in 1997 the APG Bulletin. APG Bulletin published 42 printed pages of discussions and replies. That is the longest discussion and reply published on a single paper in its entire history of over 100 years. So things happen when you address a very controversial issue. The next controversy. This is sequence stratigraphy. Exxon and the geologists like Peter Vail, Bob Mitchum, they studied sequence stratigraphy. They came up with this model using seismic profiles, wireline logs, and so on. You see this big mounded geometry of the bidirectional downlap. You see them in seismic profiles. They called it basin floor fans. And they said, if you drill them, they will generate turbidite sands, good reservoirs, and so on. Then we at Mobile, there were about 10 people worked on this project for 3 years. That includes some other well-known names like Jed Demuth, Roger Block, and Hodgkinson from London, and others, and so. We published this paper in the APG Bulletin. It's called Basin Floor Fans in the North Sea, Sequence Stratigraphic Models versus Sedimentary Fish. What we did is very simple and straightforward. We went to 10 field areas. We studied 50 wells. We described 12,000 feet of core. That's a lot of cores. And we came up with sandy slums, debris flows, bottom granules. So this is a monumental task dealing with this 3-4 years working on them. I'll just show you one example of how things look like. This is the Faroe Basin in the Atlantic. This is Iceland, Norway, British Isles. The basin is here. This is the seismic geometry of one of the sequences in the Faroe Basin. You can see the mounded geometry. And theoretically, if you drill all this, you should encounter turbidite sands and so on. So we drew this and we took core from this. This is how the core looked like. But I'll show you two photographs, one here and one here. This is what you see. Mudstone is slump form. It's not turbidite. It's a contorted slump in sandstone. The sand injection. These are not turbidites. And you have reworked sands. But the important point is these are below seismic resolution. They're just a few centimeters depth. You can't see these in seismic profiles. You need core. This is why if you going to work for an oil company, always insist on taking core. If you want to do geology and sedimentology, you need rocks. So in this case, we calculated 92% slumps and debris flows, 8% bottom current deposits. Again, breakup of orthodoxy. The problem is no longer academic. Some of the oil companies went and drew these mounds and they encountered mud. So this has become an economic problem. So when the UK Department of Trade and Industry, that's the government organization, they read my paper, they wanted me to come and give them a special presentation I did. Then they said it should be broadcast to all the oil company people in Europe. So they invited me to conduct a deep water core workshop in Edinburgh, Scotland. They invited oil company representatives from all over Europe, Italy, France, England, Scotland, some people even from Nigeria, some from America, and so on. And they could not believe what you see in seismic and what you see in the core. So they were all so proud and happy to have that workshop. And they wanted me to run it again. I did one more time in 1997. So they liked it so much, they gave me this fossil as a gift. I still keep it. The next orthodoxy is the Bama sequence. This is the late Arnold Bama. I took a picture of him in 1988 during the Confan meeting in Parma, Italy. He did his PhD in southern France, and he came up with this turbidite facies model called, this is the five division in a single bed. The A division is the graded or massive, report B division, report C division, and so on. And he proposed, in a lateral sense, if you see this A division that shows the proximal part of a submarine fan, if you see the D division, that the distal part of a submarine fan. Oil companies like this because you can use this as a predictive model of reservoir fishes. This model works only if the Walther's law of phase is applied. That means there should not be any break or hiatus. It should be a continuous sequence. Then the model is appropriate. Now remember, this was done in 1962. At that time, we didn't know much about deep water tidal currents and other processes and so on. So I wanted to keep that in mind. Bama was perfectly reasonable to introduce this model in 1962 because we didn't know much about deep water processes. After he published, there are other people who came and said the A division can be explained by other than turbidity currents like debris flows, grain flows, and so on. So it has become very controversial. Then other authors, Leclerc and Arnott, said there is no explanation why the A division become B division. Nobody conducted experiments. Nobody can prove that this really exists, that this happens. So it's a controversial issue. On top of it, when you look at rock, core, or outcrop, all you see is just a ripple bed. Is it a Bama sequence? Walker published a paper in '65 and said, yes, you assume that all 5 divisions were deposited. Then you assume that the top and bottom were cut out, leaving the middle ripple bed. So that's an assumption-based interpretation. If you start assuming things, you can assume anything you want in geology. It should be observation-based. These authors, like Hollister, claim they looked at the same kind of ripple bed. They interpreted as contourized, tidalized, barytonite. This is all observation-based. I'll show you a couple of examples. This is the evening back. I studied, published in the AAPG in 1993. When you look at the core, you see the starred ripples. I can't call that as a Bama C, assuming top and bottom are cut out. Similarly, you see the flacer bedding. I can't call this a Bama TC. So I was looking for more evidence to understand how these things form. When you look at the Gulf of Mexico, there is the loop current coming in and coming out. My study locality is located here. But these loop currents, they have underwater photographs. They form ripples. But these loop currents are not turbulent currents. So I proposed those ripples I saw, they were formed by bottom currents. Then go to the deep water masses. These water masses going all over the place, and they form deep water bottom currents in some locations. I'll show a couple of examples. This is near Mozambique. This is the AABW, that's the Antarctic bottom water. They form ripples. They're not turbulent currents. These are ripples formed by contour currents according to Hollister, and they're not turbulents. He didn't use the Bama sequence. This is Piper and Briscoe near Antarctica. They call these lenticular laminae as contourites. They didn't use Bama sequence, calling top cutout, bottom cutout Bama sequence. Then this De Castro and others, they studied core from Gulf of Cadiz. They said these are bottom current reward sands. So the next topic is the tidal currents. Chapman and others measured currents, up canyon and down canyon currents at various depths, and they correlated that with the tidal chart. They matched perfectly. So they suggested these currents going up and down submarine canyons, they are tidal currents. Using that knowledge, I was studying the Ida field of Nigeria, and we have a large canyon. We have core. When you look at the core, these are major slumps. And the same, they are interpreted with the sands with double mud layers. I didn't call that as a Bama TB division. I call them a double mud layers. You can explain them by deep tidal currents. There are papers published by Visser and other in 1980 geology. So there are tidal currents. They do form in deep water sequences. Now when you go to the Krishna Godavari basin, that's KG stands for Krishna Godavari. This is the RMS amplitude seismic map, amplitude map. I'll show this well number 2. The next, there's a large canyon. We have well number 2. When you look at the core, this is the study I did for as a consultant for Reliance Industries. And this is published in the Journal of Sedimentary Research in 2009. My co-authors are Sanjay Srivastava and Bhagwan Das. Both of them were working for Reliance at that time. And when you look at the core, this is what you see. You have discrete ripples. You have double mud layers. They are formed by tidal currents. Then go to the Andaman Sea. You see the internal waves. NASA has published so many satellite images of internal waves. When you go to Pacific and the Horizon Guyot, there are internal waves at 1,000 meters water depth. These are undersea mountains. This is the Horizon Guyot. When you look closer, they have established there are ripples on these. But geologists don't pay much attention to these things. So I published a paper in the AAPG bulletin called modern internal waves and internal tides along oceanic pictoclines, challenges and implications for ancient deep marine baroclinic systems. Particularly when these things exist, we should apply uniformitarianism. We should try to understand how they form and how we can recognize them in the rock. They exist, obviously, but there are no publications. So we always hung up on one thing: turbidity currents, turbidite, submarine fans. I think we have to branch out, open our mind a little bit. Finally, about the Bama sequence, he did his PhD in the Piracava area. This is the city of Nice, this is the Mediterranean Sea. And there's a large road cut. From Mobile, we had 3 sedimentologists, Dick Mayola, Roger Block, and myself. We went to this area. We studied the same rocks on Obama study we measured. I'll show a couple of examples how they look like. I published this in Earth Science Reviews and in 2002. This is also studied by Pickering and Hilton. They published a book. So this is a very well studied unit. So this is unit 7. This is how the rock look like. When you look closely, they show inverse grading. Large floating clast. Its internal pockets of gravel. These are no longer a single bed, they are amalgamated units. Remember in the beginning I was talking about Walther's law, no hiatus, and so on. These examples show this sense of highly complex. They were deposited by mass transport, debris flows, slumps, and so on. You can see a large packet of gravel coming from there. You can't explain these by normal turbidity curves. And you see that we can call them gamma B, that's what he did. But when you look closely, they are double mud layers. I'll show you closer. You can see the double mud layers like a railroad track going all the way across the outcrop. These are formed by tidal currents. But also in the same sequence, we see the sigmoidal bedding. This is how the sigmoidal bedding look like. And you see the inverse grading. You can't explain these by turbidity currents. And we have tidal bundles, very, very much like that. So the Bama sequence is a very complicated thing. When he studied in 1962, at the time it was reasonable to introduce the model that he did. But in 2020, it is not reasonable to apply that old model today because we have known so much about the undersea process like contour currents, tidal currents, volatile currents. We can simply close our mind and say they don't exist and keep on applying the Bama sequence. I think it's time to abandon and break the old ideas and move with the new. Then we have to know what's going on. When in 2004, the Indian Ocean tsunami hit southeastern part of India. That affected a lot of little towns, including my hometown. This is important to understand catastrophic events in applying the uniformitarianism. I proposed this model in Journal of Sedimentary Research. After the earthquake, you form the tsunami waves. They come, they transform, and they go back. When they do, they emplace large boulders like this. This is published by Follick and others, Tongatapu Island in Southwest Pacific. The scale is 2.5 meters. So this is almost about 8 or 9 meters tall. Large boulders emplaced by tsunami. Can you imagine if this thing is under the surface? Would you interpret that as a tsunami deposit? This is where we have to pay more attention to these catastrophic events if you're really serious about interpreting the ancient rock record. Then, hybrid flows. Houghton and others published a paper in Marine and Petroleum Geology. They said when the gravity flows undergo transformation, they use the word hybrid event. This is a problem because flow transformation and hybrid event beds, they are not one and the same. I'll show you why. If you go to the Cambridge Dictionary, if you don't like Cambridge Dictionary, if you go to Oxford Dictionary, they all say the same thing. The word hybrid, derived from the Latin word hybrida. What that means is you take two different species, could be in plants and animals or geologic processes. When you merge, you form a hybrid third species. For example, in animals, you take a horse and it mates with a donkey, it generates a mule. That's the hybrid offspring. That's true hybrid. You take a debris flow and it moves down and it may transform into turbidity current. Now this is flow transformation. This is not hybrid flow. This is just the opposite of hybrid. But these authors keep publishing papers calling this as a hybrid. A genuine hybrid flow, you need two different processes like this one. I published in the APG bulletin. A true flow transformation is like this one. I showed you from the Flume experiments, upper turbidity current, lower debris flow, then that eventually become turbidity current. This is from Norum and others, 1990. We have come to the end of the case study. This is the last case study 35. This is on hyperpersonal flows. When the river enters a basin, and if the density is larger than the basin water, they sink and they form hyperpersonal flows. They easily die out. They do not travel all the way across the shelf and then form submarine fans. At least nobody has yet documented that this happens. Yes, there are hyperpersonal flows, but they are very weak. So, in 2016, there was a paper published by Steele and others in the GSA bulletin. They said these hyperpersonal flows transport sand across the shelf and form submarine fans. But they did not produce any convincing evidence. So I wrote a comment on the paper, submitted to the GSA bulletin. I waited for 3 months. Normally in 3 months, journals make a decision to accept or reject. So I called the journal and the journal people said, the editor is too busy to handle my manuscript after 3 months. So I thought that was strange. I immediately withdrew my manuscript. I did not want to wait any longer. The next 1 year, what I did was, I thought this issue is a serious one. So I spent the entire year studying Yellow and Yangtze rivers in China. Why Yellow River? That is the best candidate to generate hyperpersonal flows. What I found was there is tidal shear front that prevent Yellow River sediment reaching deep sea. Similarly, bottom currents prevent hyperpersonal reaching deep sea from the Yangtze. So I published this in 2018 in the Journal of Paleogeography. People got really angry at me and they were very upset. And there were 2 major discussions, there were other discussions. And in 2019 to 2020, because of this controversy and so on, I published 6 articles on hyperpersonal flows. This is all started with submitting a simple comment. The editor not able to review or get it reviewed and publish or reject led to this. This is one of the good examples of turning obstacles into opportunities. Then, 2 months ago, the Journal of Paleogeography gave me a top journalism award. This is based on Science Citation Index of these following articles I published in there. One on submarine fans, one on landslide problem, one on seismic problem, one on soft sediment deformation fractures, one on hyperpicnic problem I just mentioned. And people are reading this and they're citing the reason because they want to see some new ideas. So it's always good to address controversies and attack them head on. So this is my conclusion slide. These are the lessons I have learned in the last 50 years. And I try to be pragmatic. I gather empirical data, field and experimental. I apply the doctrine of uniformitarianism and avoid phases models like the Balmer sequence that just leads to groupthink. And I try to break up orthodoxies if necessary. Not always is necessary. And face controversies head on and debate issues. Don't shy away from them. Turn obstacles into opportunities. And I like to acknowledge particularly people like Mobile Corporation and Mobile Corporation, St. Anthony Falls Lab, Reliance Industries, Research Institute of Petroleum, PetroChina, Island Natural Gas Corporation, Professor Santana Banerjee, who is also the head of the Department of Earth Sciences at IIT Bombay now. He has been kind enough to invite me. And Piyush Srivastava, he has been very helpful. And the technical team that put together this PROTOLITH 20, they have been very helpful. And I want to thank all of you PROTOLITH 20 participants during this talk. And I want to thank you all. I wish you best wishes for 2021. Thank you.
Thank you so much, sir, for such an enlightening talk. You continue to inspire us with your groundbreaking research work and unorthodox outlook. Now we will address some questions from the viewers. Should I go on?
Carry on.
Okay. So the first question is, are there any other basins where oil is formed from coal? Any other examples?
Any other examples of what?
Where oil is formed from coal.
Gippsland Basin is probably the best example. Remember, I did that study in 1982. I haven't kept up with the literature on that particular issue. I'm sure there are other basins, but I can't say using examples.
Okay. So should I
But
ask?
it is possible, as I showed, if the coal had the right materials, like the resinite and other hydrogen-rich components, I see no reason why they cannot generate oil from coal. But I do remember vaguely there are some recent papers from the Middle East. They were trying to connect oil to the coal source and so on. Yeah, go ahead, next question.
Thank you, sir. So the next question is whether the classical fine-grained turbidites have formed any reservoirs anywhere in the world.
Fine-grained turbidites, okay. When you deal with deep water sedimentation, let me back off here. Deep water sedimentation in the 60s and 70s, we used to think that the turbidity current is the most dominant process in the deep sea. and they form submarine fans. And that was the reason Arnold Balmer proposed these Balmer sequence. Since then, we have learned that the deep sea is a highly complex environment where you have gravity flows, where you have bottom currents, and of course there are tributary currents. What happens when there are deposition? It's a mixture of all these processes into an amalgamation of complex species. So when you ask, can fine-grained turbidites form oil? I can say yes, but not by itself. It is in association with other species. So because it's no longer possible to say this reservoir is purely from fine-grained turbidites or fine-grained dendrites or fine-grained bottom current deposits. It's a mixture of all these. This is why the deep water sedimentation is getting more and more complicated. In fact, I was talking about the baroclinic currents. Nobody's talking about them, or what kind of structure they form, how they look like in the sedimentary rock record. In fact, I can't think of any example of an ancient internal wave deposit or internal tide deposits deposited by baroclinic currents. So we are still in the very early stage of understanding deep water sedimentation.
Okay, thank you, sir. Sir, we are aware that you have studied the Krishna Godavari basin. So, we wanted to ask whether the deep water reservoirs in KG basin are turbidites or not.
Yes. Okay. If you talk to the sequence stratigraphy people, they would say they are turbidites. I am a rock person. All I do is study core and outcrop. That's what I try to show in this presentation today. When I look at the core from the Krishna Godavari basin, it is published, we have documented in great detail in the Journal of Sedimentary Research. It is composed of sandy debris flows, sandy slums, there are sand injections, and there are tidal currents. There are very few, I would say less than 1% may be turbidites in the Krishna Godavari basin.
Thank you, sir.
That is based on rocks, not seismic.
Okay, sir. So the fourth question is, how can we differentiate hybrid and flow transformation type?
You cannot. You cannot. I'll explain this a little bit more. When you talk about flow transformation, say for example, we have done this experiments in flume experiments. You introduce a debris slurry. What happens? It starts off as a debris flow. Then it transforms into stratified flows into a lower sandy debris flow and then upper turbidity current. Maybe I can go back to the slide if you don't mind. Let's see whether I can go back. I had a slide I wanted to, anyway, the slide I wanted to show is this. What is that? I'm trying to go back to some other slides so I can show. But anyway, I can answer the question without the slide. In that experiment, we have seen flow transformation going from stratified flows into pure turbidity. What happened? These flow transformation occurs in stages. But in the rock record, what happens? what is preserved in the rock record is the final moment of deposition. If there is a debris flow that's depositing at the final moment, that's the only thing you'll see in the rock record. You will not see any evidence of what happened to it during transformation, flow transformation, before it was deposited. In other words, the deposit represents only the final moment of deposition. That's it. You can say it's a turbidite or debrite or whatever it is. That's it. You cannot say anything about flow transformation by looking at the deposit. Let me give you a human analogy. In India, people talk about reincarnation. Let's suppose there is a geologist today. Can you tell whether that person was a geophysicist or a geochemist in the previous life? Cannot. The same thing with the rock deposits. You cannot tell flow transformation by looking at that deposit. Did we answer the question?
Yes, sir. Thank you so much. Sir, we have three more questions. How does fluid type, such as air, water, oil, affect the nature of sequence in turbidite?
Would you please repeat that?
Sir, how does fluid type, such as air, water, or oil, affect the nature of sequence in turbidites?
I'm not actually following that. You are breaking up. I'm not able to clear the whole question.
Sir, I'm repeating again that how does the fluid type, such as air, water, or oil, affect the nature of sequence in turbidites?
Okay. First of all, what is a turbidite? Turbidite is a deposit of a turbidity current. I mentioned to you turbidity current is a Newtonian flow. It's turbulent in state. When they deposit from turbulent suspension. That's the normal course of deposition. Your question is, no matter what the medium is, that is the physics involved in depositing. So there is no, this like the Balmer sequence A, B, C, D, E, such things don't exist. They exist only in publications. So if you're thinking about the vertical sequence with 5 divisions in your turbidite, they don't exist.
Okay, sir, thank you so much. Then we have another question. Is hybrid flow affected by the type of flow? For example, hyperpicton nature of flow?
Hybrid flow affected by hyperpicton flow. Is that the question?
Yes, sir. Like the nature of flow.
You are mixing two complicated topics here. My view is hyperpicton flows, they occur very close to the shoreline. It shows shallow water. The hybrid flows I'm talking about, they occur in deep water. Like a gravity flow coming down slope, and another flow coming at right angle, intersecting. They occur in a continental slope, maybe at the base of slope, or even near the top of the slope. Whereas the hyperpicton flows, they occur very close to the shoreline. So these two things are two completely different settings. One is in shallow water, one is on the deep water. So I don't know how they can affect each other.
Okay, and sir, the last question is, how can we interpret the lunar retreat from the tidal rhythmites?
Lunar cyclicity.
Yes, sir.
There are papers published, they actually count the tidal rhythmites, they go into the neap spring cyclicity and so on. There are so many papers published. In fact, there are papers published by Rajat Mazumdar. He used to work for Indian Statistical Institute. Now he's in somewhere in Indonesia, I think. Anyway, there are so many papers published. It is possible you can count them systematically and try to come up with the lunar cyclicity. Yes, it is possible.
Okay. Thank you so much, sir. Now I would request Professor Shantanu Banerjee to conclude the session.
Okay, thank you, Mohit. And thank you, Professor Shanmugam. So this was a quite elaborate speech with more than 100 slides, and so I'm sure that students are benefited by this. So many case studies from across the world, and we are really thankful to get you for this PROTOLITH program. And so your speech was the inaugural program of the second day of this PROTOLITH. And so with that, I thank you once again and want to conclude this session. And next time, when the things become normal, we all want to see you physically. At IIT Bombay, we want to hear you at IIT Bombay itself. So with that, we can conclude this session. Okay, thank you.
Thank you, Professor Banerjee. Thank you for inviting me. And I just want to make one final comment. This conference, the symposium, is on protolith. That's you want to understand the original rock. So if you're looking for that, in terms of IIT protolith, I am the original protolith. I went to IIT in 1965. So if you want to cite me as the original protolith, I am here.
Okay, thank you. Thank you.
Thank you.
Bye.
Bye. Vaidi?